The night sky, a celestial tapestry of twinkling stars and wandering planets, has captivated humankind since time immemorial. In ancient Greece, philosophers gazed up at this cosmic ballet and pondered the fundamental nature of the universe. These early thinkers, driven by curiosity and a thirst for knowledge, laid the very foundation of physics, the study of the fundamental constituents of the universe and the laws that govern their behavior. Thales of Miletus, often hailed as the father of science, sought natural explanations for natural phenomena. He challenged the prevailing notion that gods and goddesses controlled the cosmos, instead proposing that water was the fundamental element from which everything originated. His student, Anaximander, furthered these ideas, suggesting an infinite, boundless substance called apeiron as the source of all things. Pythagoras, known for his mathematical theorem, saw the universe as an ordered, harmonious system governed by mathematical principles. He believed that numbers held the key to understanding the cosmos, and his ideas influenced generations of physicists and mathematicians. Empedocles proposed four fundamental elements: earth, air, fire, and water, that combined in various proportions to form all matter. These early Greek philosophers, though limited by the technology and knowledge of their time, embarked on a quest to comprehend the cosmos through reason, observation, and contemplation. Their ideas, passed down through generations, laid the groundwork for the scientific revolution that would transform our understanding of the universe centuries later. The fall of the Roman Empire ushered in a period of intellectual stagnation in Europe, often referred to as the Dark Ages. While advancements in mathematics, astronomy, and physics continued in the Islamic world and the East, Western Europe experienced a decline in scientific inquiry. The dominant force during this period was the Catholic Church, which emphasized religious dogma over scientific investigation. However, amidst the intellectual shadows, embers of scientific thought flickered. Scholars in monasteries preserved ancient Greek and Roman texts, safeguarding knowledge that would later fuel the Renaissance. The Church, despite its emphasis on religious doctrine, fostered some scientific pursuits, particularly in areas like astronomy, which served to develop calendars and determine religious holidays. One notable figure from this era was John Philoponus, a Byzantine scholar who challenged Aristotle's theories of motion. He argued against the idea that a vacuum was impossible and proposed that projectiles continued to move due to an imparted force, an idea that foreshadowed the concept of inertia. Despite these isolated sparks, progress in physics during the Middle Ages remained largely dormant. It was not until the Renaissance, a period of renewed interest in classical learning and a spirit of intellectual curiosity, that physics would once again emerge from the shadows. The Renaissance marked a profound shift in European thought, a reawakening of intellectual curiosity and a challenge to established dogma. This period, known as the Scientific Revolution, witnessed a dramatic transformation in the way humans viewed themselves and their place in the cosmos. It was an era of groundbreaking discoveries, revolutionary theories, and a bold new approach to understanding the natural world. The invention of the printing press played a pivotal role in this intellectual revolution, allowing for the widespread dissemination of knowledge and ideas. Nicholas Copernicus, a Polish astronomer, challenged the long-held geocentric model of the universe, which placed Earth at the center with his heliocentric theory. He proposed that Earth and the other planets revolved around the Sun, a radical idea that shook the very foundations of astronomy and challenged the Church's teachings. Johannes Kepler, a German astronomer, built upon Copernicus's work, using meticulous observations to derive his three laws of planetary motion. These laws, which accurately described the elliptical orbits of planets around the Sun, provided a more precise mathematical framework for understanding the solar system. Galileo Galilei, an Italian astronomer, physicist and engineer, made groundbreaking observations with the newly invented telescope. He discovered the four largest moons of Jupiter, observed the phases of Venus, and studied sunspots, providing further evidence for the heliocentric model and challenging the Aristotelian view of the heavens as perfect and unchanging. If the scientific revolution was a symphony of ideas, then Isaac Newton was its masterful composer. Born in England in 1643, Newton was a polymath who made groundbreaking contributions to mathematics, physics, astronomy, and optics. His work laid the foundation for classical mechanics and revolutionized our understanding of the universe. In his magnum opus, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, published in 1687, Newton introduced his 3 laws of motion, which describe the relationship between a body and the forces acting upon it. These laws, still considered fundamental to physics today, explained everything from the motion of everyday objects to the orbits of planets. Perhaps Newton's most profound contribution was his law of universal gravitation. Inspired by the apocryphal story of an apple falling from a tree, Newton realized that the same force that pulled the apple to the ground also governed the motion of celestial bodies. His law stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between their centers. Newton's work unified the heavens and the earth, demonstrating that the same physical laws applied throughout the cosmos. His laws explained the tides, the precession of the equinoxes, and the trajectories of comets, providing a comprehensive framework for understanding the universe that would dominate physics for centuries to come. Section 5. Electric whispers, magnetic fields, unifying forces. The 18th and 19th centuries witnessed a surge of discoveries in the realm of electricity and magnetism, phenomena that had intrigued natural philosophers for, centuries. Benjamin Franklin, an American polymath, famously conducted his kite experiment in 1752, demonstrating the connection between lightning and electricity. His work laid the groundwork for understanding the nature of electric charge and paved the way for the development of lightning rods. Charles-Augustin de Coulomb, a French physicist, formulated Coulomb's law, which quantifies the electrostatic force between 2 stationary electrically charged particles. His work provided a mathematical framework for understanding the behavior of electric charges and laid the foundation for the study of electrostatics. Michael Faraday, an English scientist who began his career as a bookbinder's apprentice, made groundbreaking discoveries in electromagnetism. He discovered electromagnetic induction, the process by which a changing magnetic field generates an electric current, a principle that underlies the operation of electric generators and transformers. Faraday's work established the interconnectedness of electricity and magnetism, paving the way for a unified theory of electromagnetism. James Clerk Maxwell, a Scottish physicist, achieved this unification in the 19th century with his elegant set of equations known as Maxwell's equations. These equations described the behavior of electric and magnetic fields and predicted the existence of electromagnetic waves which travel at the speed of light. Maxwell's work not only unified electricity and magnetism, but also paved the way for the development of radio, television, and other technologies that rely on electromagnetic waves. Section 6. Einstein's Universe, a Symphony of Space and Time. As the 19th century drew to a close, physics seemed to be approaching a state of completion. Classical mechanics, thermodynamics, and electromagnetism had been remarkably successful in explaining a wide range of phenomena, from the motion of planets to the behavior of light. However, a few nagging anomalies and unexplained experimental results hinted at a deeper, more profound physics waiting to be discovered. Enter Albert Einstein, a German-born theoretical physicist who would revolutionize our understanding of space-time, gravity, and the universe itself. In 1905, while working as a patent clerk in Bern, Switzerland, Einstein published 4 groundbreaking papers that would shake the foundations of physics and usher in a new era of scientific thought. One of these papers introduced his special theory of relativity, which challenged the absolute nature of space and time. Einstein proposed that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is constant for all observers, regardless of their relative motion or the motion of the light source. This led to the startling consequences of time dilation, where time slows down at higher speeds, and length contraction, where objects appear shorter in the direction of motion at relativistic speeds. In 1915, Einstein published his general theory of relativity, which provided a new explanation for gravity. Instead of viewing gravity as a force acting at a distance, as Newton had, Einstein proposed that gravity arises from the curvature of space-time caused by the presence of mass and energy. His theory predicted the bending of light around massive objects, a phenomenon later confirmed by observations during a solar eclipse in 1919, propelling Einstein to international fame. Section 7. Delving into the quantum realm, a new physics. As Einstein was reshaping our understanding of the cosmos on a grand scale, a revolution was brewing in the microscopic world of atoms and subatomic particles. Classical physics, which had reigned supreme for centuries, proved inadequate to explain the strange and counterintuitive behavior of matter at the atomic level. This led to the development of quantum mechanics, a revolutionary theory that would forever change our understanding of the nature of reality. In 1900, Max Planck, a German physicist, proposed that energy is quantized, meaning it can only exist in discrete packets, or quanta, rather than as a continuous spectrum. This radical idea, which contradicted classical physics, successfully explained the spectrum of black-body radiation, a problem that had puzzled physicists for years. In 1924, Louis de Broglie, a French physicist, proposed that matter, like light, has wave-like properties. This wave-particle duality, a central concept in quantum mechanics, suggests that particles, such as electrons, can exhibit both wave-like and particle-like behavior. Erwin Schrödinger, an Austrian physicist, developed a mathematical framework for describing the wave-like behavior of particles, known as Schrödinger's equation, which became a cornerstone of quantum mechanics. Werner Heisenberg, a German physicist, introduced the uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. This inherent uncertainty, a fundamental aspect of the quantum world, challenged the deterministic view of classical physics and introduced an element of probability into our understanding of the universe. Section 8. The cosmos beckons modern physics and the universe. The discoveries of the 20th century, from Einstein's theories of relativity to the development of quantum mechanics, revolutionized our understanding of the universe, revealing a cosmos far stranger and more wondrous than previously imagined. Armed with these new tools, physicists embarked on a quest to explore the vastness of space and the enigmatic nature of matter, pushing the boundaries of knowledge and uncovering profound mysteries that continue to captivate scientists today. Edwin Hubble, an American astronomer, made groundbreaking observations in the 1920s that transformed our view of the cosmos. Using the powerful Hooker telescope at Mount Wilson Observatory in California, Hubble discovered that the universe is expanding, with galaxies receding from each other at a rate proportional to their distance. This discovery, known as Hubble's law, provided the first observational evidence for the Big Bang theory, which describes the origin of the universe as a hot, dense state that has been expanding and cooling ever since. The development of particle accelerators, powerful machines that smash subatomic particles together at incredible speeds, allowed physicists to probe the fundamental building blocks of matter. In the 1960s, physicists developed the Standard Model of particle physics, a comprehensive theory that describes the fundamental forces of nature, except gravity, and the elementary particles that make up all matter. The Standard Model has been remarkably successful in explaining a wide range of experimental results and predicting the existence of new particles, such as the Higgs boson, which was discovered in 2012 at the Large Hadron Collider, LHC, at CERN in Switzerland. Section 9. Unraveling the tapestry of reality, the future of physics. As we stand on the precipice of the 21st century, physics continues to push the boundaries of knowledge, seeking answers to some of the most profound questions about the universe and our place within it. While we've made remarkable progress in understanding the fundamental constituents of matter and the laws that govern their behavior, many mysteries remain, beckoning future generations of physicists to unravel the secrets of the cosmos. One of the biggest challenges in modern physics is to find a theory of everything, a single framework that unifies quantum mechanics and general relativity, the two pillars of modern physics that currently seem incompatible. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels, while general relativity describes gravity as the curvature of space-time caused by mass and energy. Unifying these two theories would provide a complete and consistent description of the universe from the smallest scales to the largest. Another area of intense research is the nature of dark matter and dark energy, two mysterious entities that make up the vast majority of the universe's mass and energy budget but do not interact with light, making them invisible to telescopes. Dark matter is thought to provide the gravitational glue that holds galaxies and galaxy clusters together, while dark energy is believed to be responsible for the accelerating expansion of the universe. Understanding the nature of dark matter and dark energy is crucial for unraveling the evolution and fate of the universe. The search for life beyond Earth is another frontier in modern physics and astronomy. With the discovery of thousands of exoplanets, planets orbiting stars other than our Sun, the possibility of finding life elsewhere in the universe has become increasingly tantalizing. Scientists are developing new technologies and telescopes to search for biosignatures, signs of life in the atmospheres of exoplanets, hoping to answer one of humanity's most profound questions. Are we alone in the universe? The journey of physics, from the stargazers of ancient Greece to the cutting-edge experiments of today, is a testament to the power of human curiosity and our relentless pursuit of knowledge. As we continue to explore the universe and delve deeper into the nature of reality, one thing is certain. The future of physics promises to be as exciting and revolutionary as its past.